astronomy guy pulls a rocket from his pocket, now ablaze from the sky. See the stars and the galaxies, explore the Big Bang, unravel through time travel, a reality sprang. You don't know where we're going, 'cause you've never been there. You don't know what we're doing till we fly through the air and beyond. Flyby the astronomy guy. Flyby.
Hello, this is Flyby the Astronomy Guy. We are going to climb on a rocket and go faster than the speed of light, go all the way back to the Big Bang. Well, not really possible to go faster than the speed of light, but we are going to do it in our minds. One way we might go into the past as if we were going faster than the speed of light is to go through a wormhole and come out the other side into the past, entering a parallel universe. What's a wormhole? Oh, it's like a tunnel in space and time, taking us into the past. The current theory of the universe says that 13.7 billion years ago, that's 1,000 million, the universe began in a tiny point. Before about 1920, the equations of Einstein began to be used to describe how the universe expanded from a point. It isn't like a bomb going off in a pre-existing space, in a location, say on the Earth, but it's like the explosion of space and time itself from a point. Get the point? Probably the best way of understanding why the universe is flying apart, why there are superclusters of galaxies that are just spreading away with time, is to think of a balloon on which you put dots. These are the masses of the superclusters of galaxies. Those are clusters of clusters, and they fly apart as the balloon is being blown up. This is a great analogy to what's going on, so let's do it. But how did we get these clusters of galaxies hanging together by gravity, and that are all different sizes and shapes. Why is the world so maximally diverse, so strange? All different sizes are represented equally. The answer is chaotic inflation. It has been discovered just in 2014 by Xiaolin Kuo and his co-workers at the South Pole that the universe produced swirls of radiation that were all different sizes and all different directions. Whirly, whirly, whirly birds. Woo, baby! Here is the BICEP 2 microwave telescope at the South Pole that Xiaolin Kuo used to discover evidence for the microwave background chaotic inflation idea. Here's a picture of Xiaolin Kuo, and he confirmed the chaos theory of a co-worker at Stanford, Andre Linde. Stanford rules, huh? Well, it was pretty interesting because when he made the observations that there was this chaos going on early on in the universe, the earliest observation of the universe, he went to Andre Linde's door and knocked on it and said, "I've got some great news for you," and he let him in, and he told him about it, and they both went kind of crazy because it was such a great confirmation of working together of theory and experiment. Swirls of energy make particles, mostly protons and electrons, which come together to make hydrogen atoms. This is the next step. This coming together creates electrons and protons making hydrogen and giving off light. And that light, when the electrons combine for the last time with protons, because they get knocked away by excessive light early on, that light has evolved into microwave radiation, which is wavelengths of about 1 centimeter long. And because of the distribution and temperatures of the microwave background, we know what the lumps of matter look like about 380,000 years after the Big Bang. This is called the recombination era. And we can kind of get the idea that there is maximum diversity in sizes of lumps and clusters of galaxies, and even in planetary objects that get formed eventually. For roughly a minute, the Big Bang, though, was hotter than about 10 million degrees, like a star, and burned 25% of its hydrogen into a heavier element, helium, by what we call nuclear fusion. It's taking small atoms and making larger ones out of them and getting energy off. So it's almost like the Big Bang was like a star for that minute, fusing hydrogen into helium. So how does this fusion work? Two lighter atoms, like hydrogen, effectively become one heavier one, like helium. And this produces energy if the atoms are small. If they were large, that doesn't work. Only breaking them apart would produce energy. So, we come to the next epoch in the cosmic dance. 13.5 billion years ago was the epoch of first light, we call it. The first stars ignite. Well, how does that work? These random-sized lumps are drawn together by gravity, and the lump is large enough it could make a star pretty quickly. And the atoms pull together, heats them to over 10 million degrees, which is what is necessary to fuse those light hydrogen atoms into heavier helium. And we have the ignition of very large stars about 200 million years after the Big Bang, or 13.5 billion years ago. Are you keeping track of the time? Whoa! Oh, baby, here we go. So, we also had some very strange objects that were formed after that 13.5 billion years, and some of them existed as long as up to 1 billion years ago. They're called quasars. What happens is that you get so many big stars formed, and the gravity is so strong that it can actually make a black hole in the center of the galaxy and draw in material and create tremendous activity. They're very active galactic cores. If a galaxy is very active, it's a quasar. Quasi-stellar object. But it's not. That's because it looked like a star at first, but then we realized, oh, it's the core of a galaxy. But there's one odd thing about the universe to be discussed yet, and that's the funny energy in space called dark energy, driving the acceleration like a compressed sponge released. And this is pretty weird because it makes the universe expand faster and faster, pushing out like that compressed sponge. And we're not sure why it's there or exactly how it behaves, although we're getting a stronger vision of that. So there's something that's a mystery. Why is this funny energy or dark energy in space there in the first place? So we now come up to the formation of the Milky Way 12 to 13.5 billion years ago. Our group of stars, held together by gravity, called the Milky Way, was formed. It looks like a pathway across the sky of milk. That's why they call it the Milky Way. But it has a lot of dark areas in there because a lot of the stars have exploded dust into the regions because they were very large stars and the gravity acted quickly to burn them up. Going forward in time, we come to 4.6 billion years ago, the birth of the solar system and the Earth. Well, isn't it interesting that our solar system and most of the planetary big bodies in it and the Earth were formed about the same time? Gravity pulled together a cloud, started making planetary bodies, and by golly, there were a bunch of them, even the moon almost at the same time, we'll find. However, after the Earth formed, 4.4 billion years ago, a little bit further into the future, a Mars-sized object went boom, hit the Earth and created vapor that condensed into our moon. We have strong evidence of that because the moon actually has similar rocks to the Earth, except that it was hot and it burned off a lot of the lighter elements. And so the content of rocks on the moon, we brought them back to the Earth, right? Happens to be basically the same as the Earth without the volatile element. 3.3 billion years ago, wow, we're moving on, an asteroid about 25 miles across, it's a lot smaller than Mars, hits the Earth and destroys any life on the surface. However, did life have to start over? Not exactly, probably, because underneath the surface, we see that happening at the poles. Underneath the surface, there are bacteria, which are forms of life, and they could evolve into more complex life. So it wasn't exactly a start over, but it was a start over for any life on the surface, evolved life that would be on the surface. We're getting up there now. 3 billion years ago is the earliest record we have of life on the Earth. In Australia, we find fossils that are solidified bacteria that were formed 3 billion years ago. So this is the oldest form of life that we've ever observed on the Earth, but it may not be the oldest because we may not have dug down in the right areas to find older forms of life. Whoop, went away. And then up to 67 million years ago. Wow, this was really big because just off the coast of Mexico, Yucatan Peninsula there, we see evidence of a very large impact by a large asteroid colliding with the Earth. It was about 6 miles wide and wiped out about 75% of the life on the Earth. And of course the dinosaurs went extinct, some of the most interesting ancient beings, if you want to call them that, wiped off the Earth. Why? Well, this impact actually created a lot of dust in the environment and global cooling, right? Oh, maybe we ought to do that to create global cooling and stop global warming. Well, leave that as it may, be that as it may. At that time, the global cooling then didn't allow the sun to come through the dust to help grow plant life, which was the food for the dinosaurs and a lot of the life on Earth. So this was a very massive extinction about 67 million years ago. All right, now we come to human-like life. The oldest human-like skeleton that we have goes back about 7 million years ago. It was walking on 2 legs in Africa. Maybe that Africa is the place that human life started on the Earth. However, our genes do not go back to this life form. They don't match. So there was evidently a wipeout and a start over again, or the evolution didn't really come to our current human form. And then there was one 3 million years ago called Lucy, again from Africa. Again, the same problem. The genes that make up the description of who we are as a life form just don't match. So where do our genes go back to? They go back about 120,000 years to our ancestors, the Cro-Magnons. In Europe, these guys and gals were hanging out, making some weapons even on occasion, and making drawings and demonstrating that they were intelligent life at last on Earth. Our genes go all the way back to them and no farther, which is interesting. What about the future of the universe? One thing that's happening is that our Milky Way galaxy is falling into Andromeda galaxy, a little bit bigger than us, and it's going to impact in about 2 billion years, and by golly, we might fall into a black hole or get our planet knocked away from the sun. Oh, all kinds of disasters could happen, but we got about 2 billion years to get life straight on the Earth. And then the sun becomes a red giant in about 4.5 billion years, consuming the Earth, burning it up. So there ain't much hope after a few billion years from now. But by then, we will have figured out how to get out of here when the problems occur. At least, I hope so. I hope we figure that out. So Flyby says, it's a cosmic dance, and it's really fun to see how the dance evolves and how we participate in it, and where we come from and where we might be going. So, bye-bye from Flyby.